We tried to create a flap mechanism that was simple and reliable, so after prototyping different actuation systems, we settled with a 4-bar linkage, driven by a DC motor through a horn attached to the shortest bar of the 4-bar linkage, and measured by a potentiometer. Attached to the flap were 3 mechanisms, with only the middle one being driven. Some refinements we made to the flap mechanism from the prototype to the one currently on the wing include manually drilling holes in the mechanism bars for more accurate holes than what the laser cutter could produce. We flipped the bars that actuate the middle mechanism so they now protrude outside of the wing. This makes the mechanism easier to manufacture and repair if anything goes wrong. It also reduced the number of spaces needed for the mechanism bars to clear bolts, decreasing the amount of play in the mechanism. The downside of this is that it will increase the profile drag of the wing. The motor was moved closer to the spar, further away from the 4-bar linkage. This was again for better access and ease of manufacture. The flap has been stiffened with an aluminium bar as the foam was not strong enough for even span-wise deflection. The flap angles given to us for the different scenarios were that all but one is to be at 0 degrees, with the final one being as much deflection as possible before stall.
When the wing mechanism is first turned on, it begins a calibration sequence. The flap moves to maximum deflection, presses the end switch, then returns until the 0 deflection end switch is pressed. This allows for the potentiometer reading to be mapped to the angle of the flap. After this process is complete, the connection to the control box is established, indicated by the blue LED. This uses RF, giving a large range capability, which would be required if the wing was going to be used on a flying UAV.
Here are the pressure tappings. They are attached to rib 5, which is located at the midpoint of the inboard flap station, as per specification.
It was found that, although the potentiometer response was linear, the mechanism made the angle response non-linear. By tabulating expected flap angle data to observed flap angle data, which was found experimentally, a linearly varying factor was added to the flap angle function, giving more accurate readings. All of them were within the 5-degree margin of error allowed. The graph shows that the new angles, which are in green, are a lot closer to the actual angles in red than when this factor was not applied.
The aileron uses an external wire pushrod connected between the control horn and the servo motor arm. This allows for fast movement as well as small incremental changes in angle.
Further improvements would involve using bearings and shafts to connect the bars instead of using the current solution, nuts and bolts. This would reduce friction, making the flap actuation smoother. We could also create a foam fairing to cover the protruding mechanism, reducing profile drag. We may change the design of the mechanism to actuate at each end of the flap in order to prevent it from flexing. We could also make a stiffer flap by threading span-wise rods through to prevent the uneven deflection that we are currently getting.
The control box had to provide the necessary functionality for wireless control of the flap installed in the wing. This was achieved using an RF module in both the control box and the wing. An RF module was selected as this would allow for the long-range communication necessary for UAV control. Connection between the wing and control box is indicated by a blue LED. 4 buttons, or alternatively a dial, are used to request a flap angle, anything from 0 degree deflection to 50 degree deflection. Improvements over the prototype included an addition of a connection indicating LED and a more versatile angle display panel.
Precise measurements of the electronic components that were to be used were recorded using a vernier caliper. Computer-aided designs of possible configurations were laser cut on 4mm acrylic, and the cut faces were assembled together. The laser cutter in Hackspace was used. For the prototype, transparent acrylic was used, whereas for the final version, black acrylic was decided instead. Also, the design was changed to a smaller box for ergonomic reasons, as more flexible wiring and a better distribution of components in the control box allowed us to do so.